Hey everyone, welcome back to The Explainer. I am so pumped to get into today's topic. We're zooming way in to figure out the microscopic, atomic level cause and effects behind how metals actually behave in the real world. We're going to demystify all those complex material science concepts and give you some really clear, actionable takeaways. So let's kick things off with a pretty fundamental question. What makes metal bend without just snapping in half? Think about a standard paperclip, right? You can bend it back and forth a bunch of times. But if you tried that exact same thing with a piece of glass or ceramic, well, it would just shatter instantly. Why is that? That whole mystery is a process called plastic deformation, and it's exactly what we're unraveling today. Here's how we're going to break it down. First, we'll look at plastic deformation and dislocations. Then, crystal slip systems. After that, we'll dive into the three main strengthening mechanisms engineers use. And we'll wrap it all up with the annealing process. All right, let's jump right into part one, plastic deformation and dislocations. Let's zoom in. Okay, to grasp how solid metal actually changes shape, you absolutely have to understand dislocations. And honestly, the best way to picture this is to think of a caterpillar crawling across a leaf. A caterpillar doesn't just slide its whole body forward all at once, right? That would take way too much energy. Instead, it makes this little hump, lifting and shifting just a couple of legs at a time, and pushes that hump from its back all the way to its front. Well, inside a metal, an extra half plane of atoms moves exactly like that. It moves step by step, breaking and reforming bonds locally rather than shifting the entire block at once. So imagine the crystal lattice. When there's an extra half plane of atoms shoved into that structure, it creates what's called an edge dislocation line. Now, when you apply shear stress, like say you're pushing the top half of the crystal to the right, that extra half plane doesn't just drag the whole top layer with it. Nope. The atomic bonds break and reform sequentially. They move that dislocation just one tiny unit step to the right, exactly like our caterpillar. This microscopic movement of dislocations is what we call slip, and it is literally the fundamental reason plastic deformation even happens.
Which brings us to part two, crystal slip systems, or what I like to call the paths of least resistance.
You see, dislocations are, well, they're kind of lazy. They always want the path of least atomic resistance. And a slip system provides exactly that. It's a specific combination of a slip plane, which is the plane where atoms are packed super closely together, and a slip direction. When stress hits the metal, it naturally yields along these highly packed superhighways, because they are perfectly aligned for easy movement. Now let's compare metals to ceramics for a second. In metals, the atomic bonds are non-directional. The atoms essentially float in this shared electron cloud, meaning dislocations can easily slide past each other. But ceramics, like sodium chloride, have ionic bonds. They're locked into a strict grid of positive and negative ions. If you try to force a slip in a ceramic, you end up shoving positive ions directly next to other positive ions. And obviously, they violently repel each other. That electrostatic pushback restricts the motion completely, and that is exactly why metals are nice and ductile, while ceramics are brittle and prone to just shattering. Okay, moving on to part three. Three strengthening mechanisms, or how we build barricades. Here's the core logic. If dislocation motion equals bending and yielding, which basically means material weakness, then to make a metal stronger, we have to build atomic barricades. Mechanism one is grain size reduction. Imagine a boundary separating two differently oriented crystal grains. When a slip plane hits that boundary, it's forced to drastically change direction. That discontinuity acts like a massive physical wall. So by intentionally shrinking the grain sizes in a metal, we create way more grain boundaries. More boundaries mean far more barricades blocking that dislocation motion, which significantly bumps up the metal's yield strength. Mechanism 2 is solid solution strengthening. This is where we mix in impurity atoms, like, say, adding nickel into copper. Because these impurity atoms are different size than the host atoms, they physically distort the crystal lattice. This creates localized compressive or tensile strains that essentially crowd the space. When an impurity happens to be near an edge dislocation, their respective strains actually kind of cancel each other out. This traps the dislocation, completely locking it in place. So suddenly, you need a massively higher shear stress to force any further movement. And mechanism 3 is strain hardening, which you probably know as cold working. Picture running a sheet of metal between two huge rollers at room temperature, just squishing it down. That plastic deformation physically multiplies the number of dislocations inside the material and crams them incredibly close together. Because these dislocations naturally repel each other, you get this massive atomic traffic jam. This, by the way, is exactly why your paperclip snaps. As you bend it back and forth, you're creating a dislocation traffic jam until the metal gets so incredibly hard and brittle that it just gives up and breaks. So, what happens when we go too far? That brings us to part 4, the annealing process, or hitting the reset button. Right, so if our strengthening mechanisms make the metal way too brittle, like our overbent paperclip, we need a way to reset it. Enter annealing. It's a heat treatment process that sequentially resets the internal structure in 3 distinct stages as things heat up. First up is recovery, happening between roughly 100 and 200 degrees Celsius, which relieves the internal strain energy. Next is recrystallization, usually between 200 and 500 degrees, where entirely new, strain-free grains actually start to form. And lastly, we have grain growth at temperatures above 500 degrees, where those fresh new grains expand, reducing the total grain boundary area. When you track this dynamically, it's honestly fascinating. During that middle recrystallization phase, the tensile strength of the metal drops off an absolute cliff. But at the exact same time, its ductility shoots way up. And the reason is simple. Those elongated, highly stressed grains from cold working are suddenly being replaced by tiny, perfectly uniform, fresh grains. The barricades have essentially been lowered. The dislocations can move easily all over again. We've successfully traded our strength right back for flexibility. So, let's distill all of this into the absolute core takeaways. Call it the golden rule of materials science. Number 1, plastic deformation happens via dislocation motion. Number 2, metals bend easily because their slip systems provide an easy path for that motion. Number 3, if you want to increase strength, you absolutely must decrease dislocation mobility, whether you do that by shrinking grains, adding impurities, or cold working. And finally, annealing reverses that whole process, trading strength back for ductility. Which leaves us with this one final, rather provocative thought. Now that you understand the microscopic levers of strength and ductility, how would you combine grain size reduction, solid solution strengthening, and cold working to design the ultimate, unbreakable alloy for a real-world engineering challenge? It's a pretty wild atomic puzzle to think about. I'll let you ponder that one until our next explainer. Keep learning, keep analyzing, and I'll catch you next time.